This video illustrates the PageRank algorithm. By the end of this video, you will learn how to apply the PageRank algorithm and use it with Kinetica. The PageRank algorithm was first used to power Google's search engine. The problem that it attempts to solve is as follows. When a user searches for a term on Google, how should the results of the search be organized so that the most relevant links are shown first? The basic principle behind the PageRank algorithm can be summarized as follows. The number and quality of links to a particular web page determine its relative importance. Let's explore this with an illustrative example. For the sake of simplicity, let's assume that the entire universe of web pages is limited to the following: A, B, C, D, and E. The arrows indicate the direction of links between these pages. Let's start by building the link matrix to map these incoming and outgoing links. Each column represents the probability of going to a different page from a particular page. So for instance, page A has outgoing links to B, C, and D. So the probability of randomly clicking on any of them is 1/3. A page cannot have self-referential links. That is, it cannot link to itself. So the probability of going from A to A is 0. And finally, we can only go to a page if a link to it exists in the page that we are currently on. So the probability of going to E from A is 0, since there are no links to E from A. We can apply the same idea to populate the rest of the matrix. Now, imagine there was a really bored person who started randomly clicking links on these pages. The PageRank is the likelihood that this person would be on any of the 5 pages on a particular click. Let's assume that the probability of them starting on any of the 5 pages is the same. So this means that they have a 20% chance of being on any of the 5 pages before the first click. Next, let's calculate the probability of being on each of the 5 pages after one click, starting with A. There are a few things that we need to know to establish the probability of getting to A. First, we need to know the pages from which we can get to A. These are B and D. Next, we need to know the probability of getting to A from these pages. We can get these from the link matrix. Next, for us to be on A, we needed to be on either B or D in the previous step. So we need the probability of being on B or D in the previous step, which in our case is 0.2. So we can calculate the probability of being in A after the first click as the probability of getting to A from B times the probability of being in B in the previous step plus the probability of getting to A from D times the probability of being in D in the previous step. This gives us a PageRank of 0.2. We can generalize this as follows. The PageRank of a page I for the nth click or iteration is the sum of all the PageRanks of pages that have links to page I for the previous iteration, divided by the number of links in each of these pages. Let's fill out a few more iterations. The PageRank algorithm usually runs for a number of iterations before the probability values converge. For this exercise, I'm going to stop at 4. But even though the PageRank values haven't fully converged yet, we can already begin to see the rank ordering, which are as follows. So now let's go back to our earlier premise of the number and quality of links. In the case of our highest rank page B, the number of links is 3, which is more than other pages. More importantly perhaps, B also has high quality links that point to it. Both the pages C and E only link to B. This means that users on these pages can only navigate to B. The link from E is particularly important since it is a high ranking web page. Now let's implement the solver in Kinetica. I've already created the graph that we just saw. The input data is pretty simple. It contains information on a starting node and an ending node, symbolizing the different links. And this is how the graph data looks in a tabular format. Now let's go to the user interface for graphs. The label for the internal representation of the graph is shown here. This is what we will solve against. Now let's go to the solver. First, let's pick the graph that I created. Next, let's pick the built-in PageRank solver. After that, let's pick a node to start the PageRank algorithm from. I will start from A. Next, let's specify a name for the output table. Now we are ready to solve, so let's solve. Okay, that worked. Let's go check out the output table. The solver node costs represent the page ranks. Let's sort that in descending order. As expected, the ranks are the same as those that we calculated by hand. The individual values are slightly different, but that's because the solver runs several more iterations. So to summarize, the PageRank algorithm uses the number and quality of links to infer the relative importance of different pages. We can use Kinetica to apply the PageRank algorithm using its built-in solver to easily rank pages.